Hello everyone, see this theorem. The theorem says that for any non-deterministic finite automata M, accepting a language L that is subset of sigma star, there is a deterministic finite automata M1 that also accepts the language L. Means that we are looking for the equivalence of a non-deterministic finite automata with deterministic finite automata. Means if there is any language L that is accepted by non-deterministic finite automata, it should also be accepted by some deterministic finite automata. Here we are representing non-deterministic finite automata with M and deterministic finite automata with M1. The fact that M1, that is DFA M1, accepts the same language as NFA M follows from the fact that for any x string, x that belongs to sigma star, extended transition function of DFA is equal to extended transition function of NFA. Extended transition function of DFA is delta 1 star q1 comma x. Q1 is the initial state of the DFA is equal to delta star q0 comma x. I hope you all remember the extended concept of extended transition function, which I have already discussed in the previous videos. So the two extended transition functions are same for reading this by reading the same string. They are giving the same output. That is the fact. We'll make use of this fact to prove the theorem. So there are some points we have to see. M1 is defined as follows. M1 is the DFA. Q1 is a set of states in M1. Q1 is 2 raised to the power Q. Remember that we are going to make the conversion from non-deterministic finite automata. Some non-deterministic finite automata with Q states, suppose it is already there, it is now converted to DFA. So the number of states the machine DFA can have is 2 raised to the power Q. If this was 2, means suppose there are some NFA with 2 states, a DFA can have a maximum of 4 states. 4 states are possible, 2 raised to the power Q. So Q1 is equal to 2 raised to the power Q, where Q is the set of states in M, where M is some non-deterministic finite automata. Q1 is the initial state of M1, which is equal to the initial state of the non-deterministic finite automata. If non-deterministic finite automata state, NFA state is Q0, in DFA we will represent this in the form of set. This initial state remains same in the DFA. The only difference is that it will be represented in the form of subset. So now the transition function. The transition function of DFA is represented in the form of delta 1. Delta 1 Q comma A. The Q is any state, A is any symbol. It will be having the formula union of R that belongs to Q delta R comma A. Now I will explain this through some example. Suppose there is delta 1 Q1 comma Q2, the subset Q1 comma Q2 comma A. It is represented by the union of R that belongs to Q1 comma Q2 delta R comma A. Replace this R by these Q1 and Q2, perform the union operation delta Q1 comma A union delta Q2 comma A. Now we'll see the transition function, that is transition of Q1 on reading A in a non-deterministic finite automata. Take the output of that is output set, perform the union with delta Q2 comma A, that is Q2 on this is Q2, which is some state in non-deterministic finite automata. On reading A, it is giving some output. We'll perform the union of these two sets. We will see these type of subsets while we'll converting the NFA to DFA. But here please concentrate on the proof. Accepting state Accepting set is any state Q that belongs to capital Q such that Q intersection A is not equal to phi, where this set Q and this A is the set of states accepting state in the non-deterministic finite automata. Once we perform the intersection, we should get any element which is not equal to phi, means at least one element is there which is the accepting state. We now prove using the structural induction on X. Let me start with the first thing, that is X, take X as null. So if you remember the extended transition function of DFA on reading null, extended transition function delta 1 star q1 comma x is delta 1 star q1 comma null, as we have taken null, x is equal to null. We all know that it will give us the output q1 only by the definition of delta star. And here we have delta q1 which is equal to q1 is equal to q0. See this. So q1 is nothing else but equal to q0, which is nothing else but equal to delta star q0 on reading null, if by the definition of delta star of non-deterministic finite automata. So by induction we have delta 1 star q1 comma x is equal to delta star q0 comma null when x is equal to null. Okay, the induction hypothesis is that X is a string satisfying the extended transition function of DFA and NFA should be same for string X. And we wish to prove that for any A, any symbol A that belongs to sigma, delta 1 extended transition function of DFA for string XA is equal to the extended transition function of NFA for the same string, that is XA. Okay, we'll have to prove this. So delta 1 star q1 comma xa is equal to delta 1 star q1 comma x comma a. This is by definition of delta star of DFA. We have already seen in the earlier lectures, which is delta 1 delta star q0 comma x comma a. This is by induction hypothesis. By induction hypothesis, these two are equal. So this becomes union of R that belongs to delta star q0 comma x delta R comma a. This is by definition of delta 1 we have just defined earlier. And this is equal to, if you remember, this is equal to delta star q0 xa, that is by definition of delta star extended transition function of NFA. So we have proved that delta 1 star q1 comma xa is equal to delta star q0 comma xa. So the theorem was saying that if there is some NFA accepting the language L, we can have an equivalent DFA accepting the same language L. So we have proved it through the proof of this equivalence of extended transition function. I hope this proof is clear to all of you. Please let me know in the comment box if you have any doubt. Now we will see subset construction to convert NFA to DFA. See the example where we have non-deterministic finite automata. What we will do, we'll make a small table here starting from Q0. Q0 was the initial state in the NFA. It is also an initial state in the DFA. Q0 on reading 0, it is going on state Q0. Q0 on reading 1, it is going on the state Q0 as well as Q1. So Q0, Q1. Remember this Q0, Q1 is the new state. Put here Q0, Q1. Now expand this. If you remember the transition function for DFA, I discussed while proving the theorem. Let me show you again. This transition function for DFA was taken as Q comma A, union of R that belongs to Q, delta R comma A. So it means that take Q0, Q1, this is delta Q0, Q1 on reading A. Here A is, there are two symbols A and 0 and 1. This is on 0. It is equal to union of, replace this R with either Q0 and then Q1. So delta Q0 on 0, delta Q1 on 0. Delta Q0 on reading 0 is going on Q0, union with Q1 on reading 0 is going to Q2. So we have state Q0 and Q2. I'll write Q0, Q2 here. Similarly, Q0, Q1 on reading 1. This on reading 1, Q0 on reading 1. I'll get the value. See the diagram, Q0 on reading 1, it is going to state Q0 and Q1, and Q0 on reading Q1 on reading 1. Write in step. This is equal to delta Q0 on reading 1 union with delta Q1 on reading 1. This is equal to delta Q0 on 1 is going on Q0, Q1 union Q1 on reading 1, Q1 on reading 1. We do not have any transition of Q1 on 1, so it is equal to 5. I'll get Q0, Q1. Now there is one new state here, Q0, Q2. Put Q0, Q2 here. Q0, Q1 is already explored, so we will just focus on Q0, Q2. Repeat the process for Q0, Q2 on reading 0 and Q0, Q2 on reading 1. Q0 on reading 0 is going on Q0. Q0 on reading Q2 on reading 0 is 5. So union with 5, I'll get Q0 only. Similarly, the same thing repeat for the symbol 1. Q0, Q2, that is Q0 on reading 1. Q0 on reading 1 is going on Q0, Q1. Union with Q0, that is Q2 on reading 1. Q2 on reading Q2 doesn't have any transition on 1, so it is 5. So I get the output Q0, comma Q1. So this becomes Q0, Q1. We do not get any new element in this space, so we will stop the algorithm. Suppose if I get a new element, I'll explore that also. But here we have now, we'll stop this, and there are finally 3 states, Q0, Q0, Q1 and Q0, Q2. So therefore, we have one state Q0, the another state Q0, Q1 and also the next state Q0, Q2. Now out of Q0, Q1 and Q2, which one was the accepting state in the non-deterministic finite automata in the original diagram? Q2 is the final phase. So final state or accepting state. So what we will do, we'll see the place where we got Q2. This is the state where Q2 is there. So we will make this as the final state. So now Q0 on will perform the transition. Q0 on reading 0, it's going on Q0. So we have this self loop on 0. Q0 on reading 1, it's going to state Q0, Q1. Q0, Q1, Q0, Q1 on reading 0 goes on state Q0, Q2 and Q0, Q2, Q0, Q1 on reading 1 stays there only. Similarly, Q0, Q2 on reading 0 is going to Q0 and on reading 1 it stays on Q0, it will go back to Q0, Q1. So this is the conversion.